Okay, talk a bit more about propulsion system.
Hello.
Hello. We have
Hello, sir.
hello. We have two different kind of propulsion system, yeah, with propeller one, propeller drive for piston engine for small aircraft, for turboprop aircraft, and with jet engine. They both create thrust by stream of air, but there are a difference. In first case, with propeller, we have a big volume of air, a lot of air, but with small speed, small increment of speed, and a big mass of air involved in this movement. In case of jet engine, we have a big speed, but a small mass of air. So, and for simulation, these two kind of propulsion system in wind tunnel, there are two different parameters. In case of propeller, we talk about disk loading factor. I don't remember what letter they use in English system, but in Russian we use B. And as we seen in this PDF from NASA, they use CJ coefficients for this. In Russian, we use Greek letter mu as subscript. C mu. But they're exactly same coefficients. So for properly simulate propulsion in the tunnel, you have take these coefficients same for real aircraft and for model. And there are a formula for these coefficients. They related thrust from engine P divided by dynamic pressure, so this term density squared speed and divided by 2, and area of propeller disc, propeller like circular, and area of this circular, what is a F. For wing typical use S, but for this propeller sometimes F. So it's disk loading factor. Thrust in newtons, area in square meters, density in kilogram per meter per square meter. So what about CMU coefficients? Maybe I need to Google it because I forgot exactly formula. Wait a minute, I'll find this formula in internet and show you. What about Google? Jet coefficient. And maybe we find a Wikipedia article or something PDF with formula. Maybe no, slightly change CRT term, yeah. Or maybe this factor expanded as formula in NASA paper, yeah? They must say about it. Or just give properly name to this factor. CM, CG, what? Trust coefficient. T by QS. So they exactly use same formula. So this CJ exactly equal that formula for B. Yeah. But so C mu is another similarity factor. And I don't need to relate to each other. Maybe in PDF about jet flaps, there are expansion of this factor because it's very important to jet flaps. C mu momentum coefficient, and there are a formula. Mass per speed per Q and S. So yeah, I can write formula for you. So firstly, CJ related also for just a different name in Russian and in English system. I need to delete this. But there are also C mu coefficients, and they same for Russian and English system. And they use don't P. They use M and V. And this point. And this point. This factor also dynamic pressure. And also area. Maybe this area. Cross section of jet. So this is the similarity factor. And you need to take it constant. So when you change scale of model from real aircraft to scale model for wind tunnel, firstly you change this F. Yeah. In real, if you have 10 times scale, yeah, real aircraft, for example, 10 meters wingspan and wind tunnel model 1 meters wingspan. So area of the propeller disc changes in scale squared value. If you scale 1 to 10, this is about linear dimension, but all areas it's equal 100. Yeah. So F changes in 100 from real aircraft to, for example, if you have propeller disc diameter 1 meters, so F equal 1. In like this. It's for real aircraft with diameter of propeller 1 meter. But when we talk about scale model, we have, for example, diameter like this. And we need to square this value for area formula, yeah? And we have 2 before this value, yeah? So this factor changes in 100. This factor slightly less change. We have different dynamic pressure in real aircraft and in wind tunnel. So we know this value from wind tunnel specification, and we know this value when linear scale down our aircraft. So we just need to find this value. And when we find this value, we able to calculate how many RPM we need to drive our propeller. What about RPM? There are another factor. Propeller thrust related to this formula. For this, I use maybe Russian notation. I'm more familiar with it. So propeller thrust P equal alpha diameter of propeller and RPM, and we need to put proper power for this values here. And I have a PDF with formula because my memory not so good, but PDF. This. We need to find this formula. Alpha then air density. We need to put air density in this formula and different power factor. This 2 and this 4. And ADD air density. So this formula for propeller. This coefficient alpha independent from propeller scale. It's same for model and for real aircraft. It depends only from geometry and the propeller pitch setting. But this coefficient changes when you scale down model, and this coefficient we need to find what RPM, what rotation per minute. We need to have same CJ. Yeah. So remember CJ formula. We have P thrust of propeller and F. So F we can write as E of pi d squared divide by 4, as I remember. So density term cancel each other. Yeah, this we have density and this density, so we have alpha. Term for d also cancel each other because 4 and square, and we remain only density squared and rpm squared. So density diameter. This also we divide by p. From this term, this cancelled. 8, 4 and 2 multiplied together, this give us 8 in upper part of formula. From this and from this. And v squared. So this term for Cj in terms of expanded thrust for different coefficients. Yeah, exactly same formula they have in books. Yeah, okay, we know speed from wind tunnel. For example, in Antonov wind tunnel, we have V equal 50 meters per second. And consider an aircraft with speed, flight speed, for example, triple. It's not real flight speed. So, for example, first speed from real aircraft, and second from wind tunnel. We know from specification of wind tunnel. Okay, scale 1 to 5. Yeah, or maybe 1 to 10 for simplification of calculation. Or it's scale. And we need to take CG same for wind tunnel and for real aircraft. Also, we know that coefficient alpha don't change. So we can relate each other. Yeah? Take this formula and write it twice. Alpha 1 t squared 1 rpm 1 okay. And with subscript 1 also. And with this formula with subscript 2, 1 for real flight, it's real, and it's 2 for wind tunnel. Diameter 2, RPM 2, and so firstly cancel terms that constant. So alpha don't change, we cancel it. P don't change, it constant. Also H don't change, it constant. Second, from scale we know that diameter 2 equal to of diameter 1. And speed, look at this number, 50 and 150. Speed equal to 1 divided by 3. So just put this in our formula. must be equal to this term became this one squared this term remained this 3 became 9 when we put in this part of formula and it so we can cancel this and this and this and this and we have a relation. This speed from aircraft from wind tunnel RPM equal to we take this value put and put 9 and a radical. Yeah. So this formula for RPM in case of aircraft with linear scale 1 to 10 and speed change 1 to 3. So we can change slightly this formula. This is really scale factor, like named S square, and this is really V1 divided by V2 square. As all values below radicals squared, we just can, as I understand, to remove it. So it's formula for calculated RPM for wind tunnel when we know linear scale. This is scale factor. We know RPM of real aircraft, and we know a difference ratio in speed between real aircraft and wind tunnel. For example, in our case, think about aircraft with RPM 3000. It's pretty real value for aircraft. Yeah? So a good calculation. Or well, and put so I obtain value near to 13,000 RPM for model. We have an increment in rotation speed 10,000. Oh no, 10 times. So we have just 3,000 for real aircraft and 31,000 for wind tunnel model. It's a very big speed, and there are limitations from strengths of propeller blades. It's very dangerous to have such big RPM. So it's possible to destroy, and sometimes it blade separated from simulator and flight in different direction and broke equipment, shoot people. It's very dangerous, such big RPM. So when experiments with propulsion simulator provided in wind tunnel, it's closed for any people. You cannot go inside when there are experiments with propulsion simulator. It's like a bullet that can at work very big speed if propulsion simulator broken and blade fly in different directions. So it's a bit calculation. Okay, this is about RPM calculation. Let's talk about different method of increment lift. So we take a bit about AN72, like this configuration. Yeah, engine in front part of wing, jet deflected by flap, and there are incrementing lift. It's called upper surface blowing. Yeah. Or just USB. There are different methods. Another method, when you put engine below wing, like in typical jet aircraft, but you put your flap in this position, and maybe engine you need to more closer to aircraft, very short pylon, and very close to lower surface, and jet stream from engine go in slot. Similar configuration, very wide slot, and air from engine must go into this slot and increase lift in flap. Maybe it's called jet blowing flap. There was experimental program in United States. They create two aircraft with different systems, left one and right one. It's first from Boeing and this from McDonnell Douglas. They create two different aircraft. They did extensional experiment and put it to museum. Take a look at this aircraft. It's pretty similar to Antonov 72 configuration. Two big engine, T-tail configuration, different flap between inner and outer section. This aircraft designed to replace Hercules aircraft C-130. Or this picture, pretty similar to Antonov 72. In fact, Antonov extensively study American documentation and take same idea for this picture, very similar to Antonov design. I have another picture in my computer. Unable to find this folder. Okay, let's take a look at another aircraft from McDonnell Douglas. This one. Or maybe this picture better. They put four jet engine very close to lower surface of wing. Wait a minute, they lowered the picture. Yeah, this picture. Scroll up. So we have a wing, four engine very close to wing lower surface, jet nozzle, and flaps with very wide slots. Hot air from jet must go into these slots and increase lift of flap. So it's another configuration from McDonnell Douglas. And this configuration give birth for C-17. Really, they related together this aircraft and this. C-17 also have engine very close to lower surface of wing, and they use same effect. Jet stream go into wide slots. Online lecture. Also, look at this picture. Jet engine very close to lower surface and wide slots, and jet exhaust from engine go into these slots and increase lift at the flaps. So main difference in first configuration, a jet stream act not only at flaps but at surface of wing constantly. But in this configuration, flaps immersed in jet stream only in lift condition. When flaps in cruise configuration, jet stream don't affect on aircraft characteristics. So this configuration have a better cruise efficiency, fuel efficiency, but maybe not so good lift. So return to sketch. There are two different configurations, and in first lift is very good, but drag also high. So poor cruise condition. In this one, lift not so good, yeah, but so in this case, when you flap up, and you have some clearance between engine jet and wing lower system, if you have any clearance, this jet don't influence on drag, and you have a better fuel efficiency in cruise condition. So this configuration, like YC 14 or Antonov 72 have a very good stall capability, but that need a lot more fuel than this. This configuration mostly for cruise. Cruise with good takeoff. Good, but not so good by this. So, and this configuration really can explore it with propulsion system simulator. So I think we can end at this point. We have recording, and this recording I'll upload to YouTube. So thanks for your attention.